Hey, welcome to The Explainer. The title for this one, Atone for Your Sins, sounds super dramatic, right? But really, it's all about getting down to the absolute nitty-gritty basics. Today, we're going to take apart the simplest sound you can imagine to find the fundamental ingredients of everything we hear.
All right, so let's just dive right in. To really get a handle on the physics of sound, we need to start with the most basic sound there is, what we call a pure tone. So what makes it tick? What are its essential ingredients? Let's break it down.
Okay, first up, we're going to look at the two properties that define the actual shape and rhythm of a sound wave as it zips through the air, and those are its frequency and its phase.
So our building block is this pure tone, and I want you to picture it as just a perfectly smooth, repeating wave of air pressure. The pressure goes up, then down, then back up again in this beautiful, clean pattern called a sinusoid. And just like the slide says, it moves with the same simple, predictable motion as a pendulum swinging back and forth. It's the purest sound you can get.
The very first ingredient is frequency. This is super simple. It just tells us how fast that wave is oscillating. You know, how many full cycles, from high pressure to low and back again, happen every single second. We measure this in hertz, or Hz, and what our brains perceive is the pitch of the sound.
Now, tied right into frequency are two other ideas, period and wavelength. And honestly, they're just two sides of the same coin. Period is all about time. How long does one full cycle take? And wavelength is about distance. How far does the wave physically travel in that one cycle? So, a high-frequency sound is going to have a short period and a short wavelength. Makes sense, right?
And this picture? Yeah, it lays it all out perfectly. The sound on top has a really low frequency. You can see how the wave is all stretched out, with way fewer cycles packed into the same amount of space. But the one below it? That's high frequency. It's all compressed with tons of cycles happening one after another.
Okay, but here's where it gets really interesting. Just knowing how fast the wave is wiggling isn't the whole story. We also have to know where in its cycle the wave gets started. And that starting point, that's called its phase.
This is such a perfect way to picture it. You know that feeling, right? If you push a swing at the wrong moment, you just kind of mess up the rhythm. But if you time your push perfectly at just the right phase, right as it hits the peak of its backswing, whoosh, you add your energy to its energy and they go higher. Sound waves work the exact same way. So take a look here. See these two waves? They're ticking along at the same frequency, same height, but they just don't line up. One is shifted just a little bit in time compared to the other. They are, as we say, out of phase.
And this isn't just some abstract physics concept. This is literally the secret sauce behind your noise-canceling headphones. What they do is listen to the noise around you, and then they create the exact same sound wave, but perfectly out of phase, a perfect mirror image. So when the peak of the garbage truck's rumble meets the trough created by your headphones, they cancel each other out. Poof, silence. It's brilliant.
All right, so we've got the shape of the wave down. Now let's talk about its punch, its power, the energy it's actually carrying, which is what our ears hear as loudness.
The amplitude of a wave is really just the size of those pressure changes. If you look at it on a graph, it's the height of the wave's peaks. A wave with a higher amplitude is pushing the air molecules with a lot more force, and we hear that as a louder sound. Simple as that. Now, pressure and intensity. They're buddies, but they're not twins. Pressure is the force, but intensity, that's the power. And here's the kicker. The intensity is proportional to the square of the pressure. Think about that. That means if you double the pressure, you actually get 4 times the energy. A tiny change in force can lead to a massive change in power.
And this relationship explains something you've probably seen with your own eyes. You know when you're playing a track with that deep, heavy bass? You can literally see the big woofer cone on your speaker moving way back and forth. It has to physically shove a ton of air to make that loud, low-frequency sound. But for a high-pitched note at the same loudness, the cone just has to vibrate a tiny bit, but super, super fast.
Okay, so we've got the shape, we've got the power, but how in the world do we actually measure loudness in a way that makes sense? Especially when you think about the incredible range of sounds our ears can handle.
Get this, the ratio of sound intensity between the quietest little whisper a human can possibly hear and a sound that's so loud it's on the verge of causing physical pain is 1 trillion to 1. I mean, just try to wrap your head around that number for a second. It's immense. So how are you supposed to measure that? A scale that goes from 1 to a trillion? It's completely bonkers. Totally impractical for, real life. You'd be writing out numbers with 12 zeros all the time.
Well, the brilliant solution to this problem is the decibel, or dB for short. It's a logarithmic scale, which is just a fancy way of saying it's a mathematical trick to squish that insane trillion-to-1 range down into something totally manageable, usually a simple scale from about 0 to 120 or so.
And this scale suddenly makes everything make sense, right? You've got a quiet forest down here around 10 dB. A normal conversation is maybe 60 or 70. And then you've got every traffic roaring by at 90. It just maps our world onto a simple, easy-to-understand scale.
And speaking of loud, you gotta love this story from rock legend Ozzy Osbourne. He famously claimed that his hearing loss was from being exposed to 30 billion decibels over his career. It's a legendary rock and roll line for sure. But, just for a little bit of context, a sound level of 30 billion decibels would have enough energy to, well, destroy the entire known universe. So maybe a slight exaggeration on Ozzy's part. Okay, so here are the only numbers you really need to remember with decibels. These are the golden rules. An increase of just 3 dB means you have doubled the sound intensity. A 10 dB jump, that's 10 times more intense. And plus 20 dB, that's 100 times the intensity.
All right, this brings us to a little brain teaser. This is going to test how you think about sound. Let's say you have one sound source playing at 40 decibels. Now you add a second, identical 40 decibel sound source right next to it. What's the new total? And I'll give you a hint. The answer is not 80.
The answer is 43 decibels. Crazy, right? But think back to that rule of thumb. When you add a second identical source, what have you done? You've doubled the sound intensity. And what did we just say a doubling of intensity is? It's always an increase of 3 dB. It's a perfect example of how the physics of sound doesn't follow the simple addition we're used to. And honestly, that's what makes it so cool.